So a covalent bond is an orbital. Orbitals can only have 2 electrons because to get 2 electrons in the same orbital, they have to have opposite spins, and you can only have 2 opposites. Okay? So if you can only have 2 electrons in an orbital, and a covalent bond is a shared orbital, it's a combining of 2 orbitals, then the covalent bond can only have 2 electrons. Okay? So for a triple bond, we actually have 3 separate bonds between 2 atoms for a total of 6 electrons. 3 pairs, 3 bonds shared between 2 atoms. Okay? Recall that a double bond has 1 sigma and 1 pi bond. If you have your model of formaldehyde in front of you, take a look at the double bond. There's a sigma bond in the middle, and there's a pi bond around the outside. So a double bond has 1 sigma and 1 pi bond. Okay? A triple bond have 1 sigma bond. Sigma, remember, is that 0 or O with a swish on it. Sigma bond. And 2 pi bonds. And pi, you know pi. Alright? I'm personally fond of peach pie. Or key lime pie. But that's not the same kind of pie. I know. Alright. Yes. Actually, that row has the same number of seats as this one. It's just they've all been pushed back. Well, no, we're not going to put another one in that row over there right now. Okay? Actually, 2 things have happened. Everybody keeps sliding their desk this way and back. So if you'll get everybody to straighten up everything later, then we'll be good.
When you sit down, you kind of...
I know how you do it. All right, so let's move on now. I want to take a look at the orbitals and how the orbitals give us the ability to make these 2 pi bonds. We're going to show you the 3-dimensional drawing, or our drawing of the orbitals, and then we're going to go and look later on at how to use electron dots to predict sort of the overall shape of the molecule too. Before we do that, take a look at your formaldehyde molecule. Pick it up and look at it. If it's arranged properly, you'll see that the sigma bond in the middle and the 2 sigma bonds on the end form a trigonal shape. See the trigonal shape?
Yeah.
There is your trigonal planar arrangement. Okay? All right. So let's look at the ground state orbital notation for carbon and nitrogen. Okay? Now these are going to, ground state means they're unhybridized, among other things. Okay, we're not going to hybridize anything when we do the ground state. All right, so this is what we learned in the last unit. Here's carbon, and carbon has 2 electrons in 1s. Then it has 2 electrons in 2s, and it has 2 electrons in 2p, but the p sublevel must have 3 orbitals. And you put 1 electron in each box and stop. If you have to pair up, you do it after you put 1 electron in each box. Okay? Ground state. We're going to look at nitrogen as well. It's in the same area of the periodic table. They're both right here in the 2p subsection of the periodic table, right next to each other. So it's going to have a full first primary energy level. 1s is only an s sublevel in the first level. Then in the second level, we're going to have 2 electrons in 2s. We're going to have 3 electrons in 2p. So 1 electron in each box, and we stop for a total of 5 valence electrons here. Carbon has 4 valence electrons, 1, 2, 3, 4. Nitrogen has 5, 1, 2, 3, 4, 5. Now, what we're going to do is we're going to hybridize in a different way. when we're doing the double bonding we've done so far anyway, we left one p orbital unhybridized. We hybridized one s and two p's, making an sp2. Okay, now when we're not hybridizing, we're hybridizing all four valence orbitals. We combined an s and three p's for sp3s. If we leave one p orbital alone, then we get an sp2. Now we're going to only hybridize two orbitals. What you think we're going to call that? sp. Or you can call it sp1, but the one is kind of like putting 10 to the first power. It's still 10, right? Okay. So we're going to leave these alone. And we're going to hybridize these. You realize we can hear you talking about your headache, right? You realize we don't want to hear about your headache? Oh, okay. I was trying not to go too deep with that, okay? All right.
Why do you leave the last two boxes?
Oh, because we're going to need two unhybridized p orbitals for a triple bond. That's why. Okay? Without two unhybridized p orbitals, you can't make pi bonds, and we need two pi bonds. So we need two unhybridized p orbitals. Okay? All right, so the question was, why do we leave two alone? And that's the answer to the question. All right. So now let's hybridize into this sp state. All right, so here's we're going to leave the first primary energy level alone because we only care about the valence level, the outermost energy level for whatever atom we're dealing with. In this case, the outermost energy level for both carbon and nitrogen is level 2. We're only going to hybridize one s and one p. So this is our hybridized set here. And we're going to call these hybridized orbitals sp. Hybridized orbitals always have a single balloon shape. Okay? Until we use them to bond, and then we get that cigar shape or that wiener shape. This is the second level. And two of these p orbitals are left alone. So we're going to do it like this. 2p. Now 2p doesn't mean I have two orbitals. 2 is the primary level. P is the type of orbital we have up here. We just happen to have two of these 2p orbitals. Okay? Now the way that you spread the electrons in, once the hybridization occurs, you treat the placement of electrons as if all these orbitals are the same thing. So all four orbitals in the valence level are put in 1, 2, 3, 4 in that fashion. Okay? Once hybridization occurs, then electrons are spread throughout the valence level. Okay? What? Got to fill up one person on each seat of the bus. Yeah. There you go. All right, so nitrogen is going to work the same way because we're going to also hybridize it into an sp state. The first primary level doesn't change because it's not the valence level. Only the valence level changes. The valence level is 2. That's the highest energy level here. We're going to combine one s and one p into this sp state, which is in the second primary level. And we're going to leave two p orbitals alone in the second primary level. That's the second primary level there. But here we have 1, 2, 3, 4, 5 electrons. So we're going to put 1, 2, 3, 4 and pair up there. So once hybridization occurs, you fill orbitals as if they're all the same thing, even though we're separating them out into separate types of orbitals sometimes. sp3s you don't separate it out, but sps and sp2s you do. All right, now, so what we have now is a hybridation state in which we have two hybridized orbitals. Those are single balloon shapes. Okay? And we have two p orbitals unhybridized, and those are double balloon shapes. Got that? All right, so this is going to get a bit more complex. So here's a carbon, and here's a nitrogen. All right? I'm going to leave one p orbital unhybridized. Remember, our p orbitals were double balloon shapes. So both on the carbon and the nitrogen, a p orbital is unhybridized. We'll make this orange. Or here in the South, sometimes people call it orange. Okay. There's a famous comedy routine called What It Was with Football, in which the comedian says, "Big orange drink." Okay. Yep. Yes. Never mind. Now, I have two p orbitals that are unhybridized though. Okay. So we're going to code this first p orbital here orange to match up to the one we've already done. The second one I've got to have it 90 degrees to this, but I need to turn it. In other words, I need to take the p orbitals will be arranged like this, like a cross. One p going this way and one going this way, 90 degrees from each other. But I need to turn it to U like this to make everything kind of fit together. All right. So what I'm going to do here is to draw this second p orbital as if one of them is coming out toward you, and one's going back behind everything. One is coming out toward you, and one's going back behind everything. Okay? So let's see. Let's make this one green. And so here's our other p orbital we just drew in there. Now, hybridized and unhybridized orbitals want to be as far apart as they can. Want to be as far apart from each other as they can be. Hybridized orbitals here and here. The nitrogen has a set of hybridized orbitals. The carbon has a set of two hybridized orbitals. They're single balloon shapes, and we need to arrange them so they're as far apart as they can be from each other. Well, that means I need, since this is on the x-axis, the y-axis, and this one's coming out toward you as if it's completely vertical, we need one that's going like this. And this is like going this way. All right? So if you want to imagine how this might be, the p orbital is this way, the p orbital is this way, and the hybridized orbital is going like this, 90 degrees from each other. That makes sense? So you got to kind of think of this in your head about what it actually is going on. I'm drawing in 2 dimensions. We're actually thinking in 3. Okay? I will. So this is a blue one. I'm going to call it. This is a hybridized orbital. So let's color code this one blue and this one blue. Okay? To match what we've done down here. Now there's one more hybridized orbital. Okay? And that would be back here on this other side. Well, it looks like a flower being flat, but remember this is 3-dimensional. One is going vertically, one's going side to side, one's going this way. Okay? Alright, let's see. Blue, green, orange. I guess I can go purple. Alright. So now this is our hybridized orbital we just color coded there, okay? Now, the sigma bond is going to be between these two hybridized orbitals. They're going to form a sigma bond because that's going to lie directly on the line between the two nuclei. It's like you were going to roast hot dogs or wieners over a fire. You take a stick and go right through the center of the wiener, right? Well, we're talking about the shape of bonds. Yep. The same way you did before. You're going to make a little knot on the end. Okay? Yes, I do. They did it in physical science?
Yeah, we did.
All right. Well, there's no reason to do it if you've already seen it. Okay, let's do this. Let's worry about this right now, okay? All right. So, These two orange balloons here are the same p orbital. Two nodes, two balloons representing two nodes of the p orbital. And the two nodes of the p orbital are going to join together side to side, forming two nodes of the same pi bond. Okay? Two nodes, two parts to the same pi bond. You could think of it like the wiener's here, and the hot dog bun has two parts going around it. You don't like that? Well, whatever. Alright. Then here's another one. Here's another set of p orbitals. So those are going to join together too. Alright? You get what's going on? Kind of, sort of. So these are joining up. These are joining up. And these are joining up here. Okay? Now then, the carbon has one hybridized orbital that can overlap with this one because they both want to have two electrons in the orbital. But this nitrogen here has nothing to share. This orbital here is full. This hybridized orbital is full. So we're not going to do anything over here with this hybridized orbital of nitrogen. It's full. We're going to leave it alone. Okay? But this hybridized orbital on the carbon would like to share an electron with somebody so it can be full. So let's give it a hydrogen to share with, okay? And so we're going to get a combination there. So let's see, this is going to be a sigma bond. Here. We're going to have a sigma bond in here. And this is going to be a pi bond.
How do you know which bonds are which?
I'm color coding them. The sigma bond has to be the one that's in, but right on the line between the two nuclei.
And pi bonds like this and everything?
Well, pi bonds are around that. They run parallel to the sigma bond, but not directly on the line between the two nuclei.
Yeah, I got it.
Okay? So that's a pi bond. This is pi. But there's two different pi bonds. This orange one's a different pi bond. What? There's two different pi bonds. The orange one and the green one. Okay, remember we have to have two pi bonds for triple bond, okay? So let's call this pi bond number 1. And that means that this is pi bond number 1, so is this one down here. Okay? Two nodes of the same pi bond. That makes this one number 2 here. Okay? Alright. So how does that all come together? Let's see. Here's our carbon. Here's our oxygen. What is the shape of a sigma bond? What? Oh, I'm sorry. You're right. I did say not CC, didn't I? I don't want to do that. Alright. So what is the shape of a sigma bond? I've done it since, for 2 days now. Actually, today's the 3rd day. What's the shape of a sigma bond? A what? It is a wiener shape, yes. So the sigma bond here is going to be wiener shape when it's done. Okay? And I'll put the nitrogen back there in a minute after that dries, okay?
So is this just a different way of drawing what we saw up there?
Well, this is showing what it's going to do. This is what it shows what happens when it does. Yes? Sure. Alright, so this orange set of p orbitals that are going to reach out and touch each other like this, okay? Then we're going to have this green orbital. So this one's got to swing out in front and go behind as well. What? Happy now?
Yes. Yes.
That was just mean. There's a song for everything. Oh, really? What? Yeah, I've heard that one. That was like from the 1960s. So I would know it. I would have been around. Yep, when the dinosaurs were still ruling the earth. See, I'm just a dinosaur in human clothing. Well, there are tiny dinosaurs and big dinosaurs. You know the raptors from Jurassic Park? Those are really oversized. The actual raptors were smaller than the ones in Jurassic Park, and most of the raptors were those little tiny ones. And there were some of those in the sequels to Jurassic Park. The little tiny raptors that just chewed the guy to death, one tiny little bite at a time. Y'all haven't watched that? Y'all don't know? Okay. Yep.
I watched the reptile movie,
All right. Are you getting the idea here, sort of, kind of? All right, sort of, kind of. Okay. Oh, well, sorry. All right, now listen. So, here's what we have. Remember the p orbitals here. Okay, here and here are 90 degrees from each other. No, they're 90 degrees from each other. They're like this. Well, I'll use the color orange here, I guess, okay? They're like arranged like this, and we just sort of tilted it. Well, let's see, the green would be here. There we go. Tilt the green one up toward you like this, and you get that like this. Okay? Huh? No, it's not 180. These two nodes are 180 degrees from each other.
Oh, I thought that's what
All right. These two pi bonds here, one orange, one blue, okay, are parallel to the sigma bond. The two pi bonds are parallel to the sigma bond. They're all running like this, side to side. But they're three-dimensionally parallel, not two-dimensionally parallel. Okay? All right, really quickly, I want to go over the electron dot formulas and the way we get to the molecular shape of this. Okay? So hydrogen has how many electron dots? Carbon has how many electron dots? 4. Nitrogen has how many electron dots?
5.
So I can share this hydrogen, and here's how we get that triple bond. There's one here, and one here. There's our triple bond. 6 electrons are shared. Going from this then to the Lewis formula where you squeeze the electrons in between. Okay? That's how you make a triple bond. Okay? In Lewis dot formulas. When we go to the electron pair shape, we want to take the sets of electrons around that central atom. The only thing we're interested in is the shape of the bonds around the central atom. Take the sets of electrons and move them as far apart as we possibly can in three-dimensional space. All the electrons between two atoms make up a set. How many sets do we have around carbon?
3, 4.
Just 2. All the electrons between two atoms make up a set. That's one set.
Okay.
There's another set. So that means we have a linear electron pair shape, because you can't get any further apart than 180 degrees. Okay? The molecular shape, or whatever shape follows this one, is you take any shared sets of electrons and replace them in the same drawing with the atomic symbol of the atom they're shared with. So this, alright, so over here, those 3 electrons are shared with this atom. We'll put that atom symbol there. Over here, these 2 electrons are shared with the hydrogen. And so now we have a linear molecular shape. Now, if there were lone pairs left, we'd have another step to go. But since we've taken care of all the pairs of electrons, molecular shape, we're done. This is the linear molecular shape. This is a linear electron pair shape. Okay? All right, last thing. We have homework.
No.
Let's see. I want you to do molecular shape of carbon dioxide. Using the method you've been taught.
Are we going to draw it?
We're going to be doing the balloon model of this and CO2 on Monday. So bring your balloons back, or if necessary, I guess get some more.